Hello everyone, welcome to SPEC eLearn, the online learning channel dedicated to chemical engineers. Hello viewers, hope you are all fine. In this video, I will be presenting the GATE previous year questions and solutions for the years 2021 and 2020. The questions we will be discussing are GATE 2021, question number 9, question number 29, question number 39, question number 46. GATE 2020, question number 9, question number 30, question number 34. I would appreciate if you subscribe to the channel. It will motivate us to produce more valuable knowledge content for your career progress. So subscribe now before you forget. GATE 2021, question number 9. In reverse osmosis, the hydraulic pressure and osmotic pressure at the feed side of the membrane are P1 and Pi1. The corresponding values are P2 and Pi2 on the permeate side. The membrane, feed and the permeate are at the same temperature. For equilibrium to prevail, the general criteria that should be satisfied is option A, Pi1 equal to Pi2. Option B, P1 equal to P2. Option C, P1 plus Pi1 equal to P2 plus Pi2. Option D, P1 minus Pi1 equal to P2 minus Pi2. Understanding the concept, the driving force for the RO process is the applied pressure. The actual operating pressure available for a given RO unit is known as the differential pressure or the net driving pressure. The net driving pressure is the difference between the feed water pressure, that is the applied pressure, and the osmotic pressure. The P1 and P2 are the hydraulic pressures and POS1 and POS2 are osmotic pressures on the feed side and permeate side of the membrane respectively. Then the net driving force will be P1 minus POS1 minus P2 minus POS2. It is given in the problem that POS1 equal to Pi1 and POS2 equal to Pi2. Hence, for equilibrium to prevail, the net driving force should be P1 minus Pi1 equal to P2 minus Pi2. Hence, the answer to the problem is option D. GATE 2021, question number 29. In a solvent regeneration process, a gas is used to strip a solute from liquid in a countercurrent packed tower operating under isothermal condition. Pure gas is used in the stripping operation. All solutions are dilute, and Henry's law Y star is equal to mx is applicable. Here Y star is the mole fraction of gas in equilibrium with the liquid phase of the solute mole fraction x, and m is the Henry's law's constant. Let x1 be the mole fraction of the solute in the leaving liquid and x2 is the mole fraction of the solute in the entering liquid. When the value of the mole ratio of liquid to gas molar flow rates is equal to m, the overall liquid phase NTU, NTUOL is given by option A, x2 minus x1 divided by x1. Option B, x2 plus x1 divided by x2 minus x1. Option C, ln of x2 by x1. Option D, ln of x2 plus x1 divided by x2 minus x1. The Mercaptelier diagram for the stripper for the case with L by G is equal to m is equal to slope of the operating line is shown in this figure. Since the equilibrium line is a straight line with slope m, the equilibrium curve and the operating line are parallel. The overall liquid phase NTU, NTUOL is defined as the integral of the inverse of liquid phase driving force. NDEOL equal to integral x out to x in dx divided by x minus x star. If the operating line and equilibrium line are straight and parallel, then referring to the figure, the driving force x minus x star is constant. Hence, on integration we get NOL equal to x in minus x out divided by x minus x star. At x is equal to x1, x star becomes y1 by m. Substituting for x star, we get the overall liquid phase NTU NOL equal to x2 minus x1 divided by x1 minus y1 by m. It is given that pure gas is used for stripping, hence y1 is equal to 0. So the overall liquid phase NTU NTOL equal to x2 minus x1 divided by x1. The answer to the question is option A. GATE 2021 question number 39. A gaseous mixture at 1 bar pressure and 30 degree Kelvin consists of 20 mole percent CO2 and 80 mole percent inert. Assume the gas to be ideal. Take R is equal to 8.314 joules per mole Kelvin. The magnitude of minimum work required to separate 100 moles of this mixture at 1 bar and 300 degree Kelvin into pure CO2 and inert gas at the same temperature and pressure in kilojoules is. For an ideal mixture of n components, the minimum work for separation can be expressed as W minimum equal to FRT sigma I to n xi ln xi, where R is the gas constant in joules per mole Kelvin, T is the temperature of the mixture in Kelvin, x1 is the mole fraction of the component I in the feed, W minimum is the thermodynamic minimum work independent of any particular process in J, F is the feed rate in moles. X CO2 is 0.2, X inert is 0.8. So sigma n is equal to 1 to 2, xi times ln xi equal to x CO2 ln x CO2 plus x inert ln x inert. Substituting the values of x, you get sigma n equal to 1 to 2, xi times ln xi equal to minus 0.3219 minus 0.1785 equal to minus 0.5004. The minimum work required to be done for separation is Wmn equal to FRT times minus 0.5004. So W minimum equal to 100 times 8.314 times 300 times minus 0.5004. So W minimum works out to minus 124.81 kilojoules. So the minimum work required to separate equal to 124.81 kilojoules. Before we move on, I would like to make a call to my dear viewers. Your SPEC e-learn channel is one-stop learning and skill development destination for your career needs. Get instant access to useful career-oriented subjects and become knowledgeable and competent. So do not forget to subscribe. Please press the subscribe button now. GATE 2021 question number 46. A distillation column handling a binary mixture A and B is operating under total reflux. It has two ideal stages including the reboiler. The mole fraction of the more volatile component in the residue XW is 0.1. The average relative volatility alpha AB is 4. The mole fraction of A in the distillate is at total reflux, the number of theoretical stages are minimum. The number of stages at total reflux condition is determined from Fensky equation. Nm equal to log xt divided by 1 minus xt times 1 minus xb divided by xb, the whole divided by log alpha average, where alpha average is a average relative volatility, xt is the distillate composition, xb is the bottom concentration. Given that Nm is equal to 2, xb is 0.1 and x average is 4. Substituting the above values in the Fensky equation for total reflux condition, you get 2 equal to log of xt by 1 minus xt times 1 minus 0.1 divided by 0.1, the whole divided by log 4. The mole fraction of more volatile component in the distillate xd equal to 0.64. GATE 2020, question number 9. Pure gas P is being absorbed into a liquid. The dissolved P undergoes an irreversible reaction in the liquid film. The reaction is first order with respect to P. Which of these following represents the concentration profile of P in the liquid film at steady state conditions? The option A and B for the question are shown in this figure. The option C and D for the question are shown in this figure. This is a problem of absorption with chemical reaction. Let me explain the concept involved before I go into the solution part. When the gas chemically reacts with a liquid or some component in the liquid, the concentration in the liquid phase is low or zero. This enhances the mass transfer through the liquid film. Hence, absorption followed by chemical reaction in the liquid phase is often used to get more complete removal of a solute from a gas mixer. If the reaction is irreversible, which is normally the case, at absorption condition, the equilibrium partial pressure is zero, that is, Y star is equal to 0. For mass transfer with chemical reactions, the absorption rate expression must account for both the gas component and liquid reactant, the chemical reaction rate, the equilibrium relationship, gas and liquid phase transfer resistances. Since the gas is pure A, there is no mass transfer resistance in the gas film. The interface behavior is different for different types of kinetic regime. That is, it depends on the nature of the reaction and the order of the reaction. In the problem given, the reaction is first order, not instantaneous, and the reaction is irreversible. So the equilibrium partial pressure of P is 0. Hence, the answer is option B. GATE 2020, question number 30. Consider the equilibrium data for methanol water system at 1 bar given in the figure below. A distillation column operating at 1 bar is required to produce 92% methanol. The feed is saturated liquid and is equimolar mixture of methanol and water. The minimum reflux ratio is option A 0.33, option B 0.5, option C 0.54, option D 1.17. Shown here is a figure of the equilibrium data given for the problem in the question. This is the Mercaptali diagram. Mole fraction of A in the feed is X of equal to 0.5 and mole fraction of A in the distillate XD equal to 0.92. From XD, draw a vertical line so that it intersects the diagonal line at point O. From point O, we draw a rectification line such that it intersects the equilibrium line at P x dash y dash. The slope of the operating line is Rm by Rm plus 1. At minimum reflux, the slope of the operating line for rectification is obtained from the graph Rm divided by Rm plus 1 equals xt minus y dash divided by xt minus x dash. Since the feed is a saturated liquid, Q is equal to 1 and x dash is equal to xf. Substituting this at the minimum reflux, the slope of the rectification line becomes Rm divided by Rm plus 1 equals xt minus y dash divided by xt minus xf. From the graph, mole fraction of vapor in equilibrium with the feed y dash equal to 0.78. Substituting these values, we get Rm by Rm plus 1 equal to 0.3333. So Rm equal to 0.5. So the answer is option B. GATE 2020 question number 34. Equilibrium data for binary mixture of E and F at two different pressures is shown below. It is desired to process a feed containing 80 mole% E and 20 mole% F and obtain a product with a quality of 99.5% purity of E. A sequence of two distillation columns, one operating at pressure P1 and another at P2, is employed as shown in the figure. Mole fraction of E in the distillate obtained from the column 1 is 0.9. This is the equilibrium data for the problem at two different pressures. If the column pressure P1 and P2 are in kPa, which of the statement is correct? Option A, P1 is 100, P2 is 20 and high purity E is recovered from the top of the column 2. Option B, P1 is 100, P2 is 20 and high purity E is recovered from the bottom of the column 2. Option C, P1 is 20, P2 is 100 and high purity E is recovered from the top of the column 2. Option D, P1 is 20, P2 is 100 and high purity E is recovered from the bottom of the column 2. The two columns are schematically illustrated in this figure. Feed with mole fraction of E equal to 0.8 is entering column 1, operating at pressure P1. The overhead from column 1 with mole fraction of E equal to 0.9 is fed to the column 2, operating at pressure P2. To find the correct answer to the problem, you should look at the equilibrium diagrams of the non-ideal systems as the one shown here. At 20 kPa, distillate produced has mole fraction of 0.9. You cannot attain pure product because the equilibrium line cuts the diagonal line and lies below the diagonal line. Further distillation produces vapor which will be richer in F. Now look at the equilibrium curve at 100 kPa pressure. From about mole fraction of 0.84 to 0.85, the K is less than 1. That is, equilibrium line is below the diagonal line up to mole fraction of 1. The vapor produced from this mixture is richer in F and hence E can be recovered at the bottom as pure component. Hence the answer to the problem is option D. Please subscribe to our channel and get updates on the upcoming courses by pressing the subscribe button. It will motivate us to produce free, knowledge-rich video content for you. With this, we have come to the end of the presentation. Please give your comments, if any, about this course after you finished viewing this video. Share with your friends and colleagues to reach out to large number of career-oriented professional students. Thank you for watching.